It's 3:15 a.m. on a Sunday, and if you are managing a 5,000-ton per day cement line, like anywhere in Rajasthan or Madhya Pradesh, you know the exact dread that comes with a phone call at that hour.
Oh, absolutely. You pick it up, and the control room operator doesn't even say hello.
Right, they just hit you with it.
Yeah, they just say, the ID fan tripped, high vibration on the drive end bearing, kiln is stopped.
And in that single second, your entire week is just gone.
Completely gone.
It
Because, a kill trip isn't just like flipping a switch back on.
It's a massive thermodynamic event.
Exactly. The refractory bricks inside that massive rotary tube, they start cooling down. The thermal profile just collapses.
And the financial bleed is immediate, right?
Yeah. You are bleeding anywhere from 8 to 14 lakh rupees in lost clinker production per event.
Mm-hmm.
And I mean, that's not even counting the astronomical cost of the emergency mechanical intervention.
It's the physical reality of heavy industry. The margin for error is measured in microns, but the machinery weighs like hundreds of tons.
Yeah, that's the brutal reality we are dissecting today.
Welcome, everyone. We are taking a deep dive into the absolute bleeding edge of industrial maintenance today, specifically looking at this massive, high-stakes ecosystem of the Indian cement sector.
And it is massive. I mean, we're talking about an industry moving over 380 million tons of material a year.
Which is just staggering to think about. But the fascinating part is that this entire colossal output, it really balances on the reliability of a few specific, highly stressed mechanical choke points.
Right. And our mission for this deep dive is to, cut through all the theoretical fluff you hear about digital transformation.
We want to look at the actual grimy, high-temperature reality of maintaining these critical assets on the floor.
Exactly. We're going to break down the physics of why these machines fail and how the current diagnostic paradigms are just fundamentally flawed.
And more importantly, how a convergence of edge AI and modern computerized maintenance management systems tools like Oxmate are completely rewriting the rules of predictive safety.
Yeah, because the focus has to remain squarely on the factory floor. I mean, theoretical data models look pristine in a corporate boardroom presentation in Mumbai, but
the truth is in the dust, right?
yes, the truth of operations is discovered in the dust, the noise, and the heat of the plant. In heavy operations, truth matters significantly more than respectability.
That's a great way to put it, truth over respectability.
Because a flawed maintenance schedule might look really respectable on a printed Excel sheet, but the physical laws of thermodynamics and mechanical stress will expose the truth of it eventually.
And usually pretty violently.
Right. You cannot negotiate with the physics of an induced draft fan.
Well, let's anchor the listener right there, the induced draft fan or the ID fan.
Yeah, for anyone operating a rotary kiln, this piece of equipment is the absolute heartbeat. Or actually, more accurately, it's the respiratory organ of the entire thermodynamic process.
Before we even touch on digital twins or predictive algorithms, we need to really map the physical brutality this machine endures every single minute.
To understand the stress, you have to visualize the flow of the process. I mean, a modern dry process cement kiln is essentially a continuous, highly controlled firestorm.
You're pushing raw meal sow, limestone, clay, iron ore through this system.
Yeah, and it eventually reaches material temperatures around 1,450 degrees Celsius to form clinker.
Which is insanely hot.
It is.
Yeah.
And to sustain that combustion and pull the suspended gases and particulates through the preheater tower, the kiln, and the cooler, you require massive volumetric draft.
And that draft is the ID fan's job.
Exactly. We are talking about an enormous centrifugal impeller. These things are often 3 to 4 meters in diameter.
So like the size of a room spinning at incredible speeds.
Right, spinning fast and pulling millions of cubic meters of gas.
It's crucial to point out that this isn't pulling clean ambient air.
Not at all. It is pulling exhaust gases that are heavily laden with highly abrasive suspended dust.
And this gets compounded significantly by the fuel source, right? Especially in the Indian context.
Oh, hugely. Plants there rely heavily on indigenous coal, which is notoriously high in ash content and sulfur.
So what does that specific chemistry do to the fan?
Well, the chemistry of that high sulfur coal is the root cause of the operational bottleneck. When you combust coal with like 30 to 40% ash content.
That's a ton of ash.
It is.
Yeah.
And when that combines with the alkalized sulfates and chlorides volatilizing in the kiln, you don't just get loose dust.
It's not just like throwing flour in the air.
No, it forms a highly adhesive, sticky particulate.
Oh, wow.
Yeah, and as this gas stream hits the heavy carbon steel blades of the ID fan at high velocity, it begins to plate out.
It sticks to the blades,
Exactly. It builds up this hard, crusty layer on the leading edges in the casing.
which creates an immediate physics problem. I mean, we all know that centrifugal fans rely on perfect dynamic balance.
They have to. If you have a 3-meter steel impeller spinning at 900 RPM, the mass distribution has to be immaculate.
But the deposition of that high sulfur dust is never uniform, is it?
Never. It might flake off slightly on one blade and just continue building up on another.
And the moment you have uneven mass distribution on a rotating body,
You generate a dynamic unbalance, and the physics equation for this is ruthless.
how so?
Well, the centrifugal force of that unbalance scales with the square of the rotational speed.
Wait, the square of the speed?
Yes. So a few hundred grams of uneven dust on the periphery of that impeller translates into hundreds of kilograms of radial force.
Just slamming into the bearings.
Right, slamming into the trunnion bearings with every single revolution.
Man, that repetitive, violent radial load, that's what shreds the spherical roller bearings, right?
Exactly. And that brings us right back to that 3.15 a.m. phone call. Bearing failure on these ID fans is documented as the single most frequent cause of unplanned kiln trip events in North Indian plants.
But here is the pushback from anyone looking at this from the outside. If the engineers know exactly what causes the buildup, and, they know the exact chemistry of the coal, why does this continuously result in catastrophic emergency shutdowns?
It's a fair question.
Right. Like, if you know a marathon runner's lungs are filling with dust, why are you running them until they collapse? Why isn't there a rigorous preventative cleaning schedule that intercepts this before the bearing gets destroyed?
Well, the intention to clean the fan is always there, but the logistics of managing that at scale break down completely when you look at the legacy tools being used.
What kind of tools?
If you look at the operational data, an astonishing 62% of Indian cement plants are still operating their maintenance scheduling through paper-based registers.
Wait, really? Paper?
Paper or fragmented, isolated spreadsheets on someone's desktop.
That's crazy. When you scale that up to a portfolio level, the sheer volume of data must be paralyzing.
It is. Take a conglomerate like Ultratech with over 24 integrated plants, or like ACC in Ambuja.
You are talking about tens of thousands of rotating assets.
It's exactly. Gearboxes, bucket elevators, ball mills, clinker coolers, and all those ID fans.
And if the health of those assets is just trapped on a clipboard hanging in a shift supervisor's office,
Proactive maintenance is fundamentally impossible. The human brain, even an entire department of highly skilled reliability engineers that cannot manually aggregate all that.
they can't correlate the degradation curves of thousands of assets simultaneously without a unified digital framework.
Exactly. Because they lack real-time, portfolio-wide visibility, the maintenance culture inevitably devolves into this run-to-failure paradigm.
It's totally reactive.
Right. It's a reactive posture dictated by the limitations of the data management system, not by a lack of engineering competence.
The engineers are doing their best with what they have.
Exactly. But they are forced to wait for a signal that the machine is dying, rather than tracking the conditions that lead to its death.
Which transitions us perfectly into the core engineering flaw of the entire industry standard, right? The reliance on lagging indicators.
Yes, the lagging indicator trap.
Because right now, the way a plant knows an ID fan is in trouble is when the vibration monitoring system triggers an alarm in the DCS.
The distributed control system, yeah. The alarm goes off, the operator sees a flashing red light on the SCADA screen, and they either trip the fan manually or it trips itself.
And relying on that vibration alarm is a fatal operational trap.
It absolutely is. We have to deconstruct what we call the PF curve.
The interval between the potential failure and the functional failure.
Right, because by the time a massive, heavily reinforced industrial fan begins to physically vibrate with enough amplitude to trigger a standard vibration sensor,
The damage is already done.
the structural degradation is already well underway. The mass of that dust has been transferring destructive kinetic energy into the bearing housing for hours, maybe even days.
The lubricating oil film inside the bearing has probably already ruptured under that extreme load.
Exactly, which leads to metal-on-metal contact, micro-spalling on the raceways, and elevated temperatures.
So, waiting for the vibration alarm is like waiting for your car's engine to catch fire before deciding to change the oil.
That is a perfect analogy.
The alarm isn't a warning, it's a death certificate for the equipment.
The structural collapse of the roof telling you the house has already burned down, the bearing life is compromised, the shaft might be scored, and you're already on the hook for the massive cost of an emergency replacement.
Plus the lost clinker production.
Right. And this reactive cycle is responsible for the industry losing an estimated 12 to 18% of available kiln hours annually.
That's a huge hit to profitability.
It is. What's fascinating here is the concept of the quiet architect in advanced engineering philosophy.
I love that term. What does it mean practically?
It means serious operational leadership requires moving upstream of the symptom. The shaking of the machine is merely the visible terminal symptom of a much quieter, invisible disease.
The localized accumulation of mass.
Exactly. If your entire maintenance strategy is anchored to managing the symptoms, you will permanently trap your workforce in high-stress, dangerous emergency recovery modes.
And we really need to linger on the human element for a moment.
I agree.
Because this isn't just a financial discussion about, optimizing MTBF or saving 10 lakh rupees.
No, it's much more visceral than that.
Right. When that ID fan trips, the massive steel casing is radiating heat. The surrounding environment is suffocatingly dusty and noisy.
And you are suddenly sending a crew of mechanical fitters right into that highly dangerous zone.
Under immense pressure from management to get the kiln spinning again.
Yeah, you are introducing fatigue, heat stress, and urgency into heavy lifting operations. The safety implications of run to failure are terrifying.
That is the ultimate consequence of the lagging indicator. It trades predictability for chaos.
And it forces the human workers to absorb the risk of that chaos. To escape this, the engineering approach has to radically shift.
We have to move from monitoring the mechanical degradation to monitoring the aerodynamic friction.
Exactly. We have to capture the leading indicator.
Okay, so let's break down exactly how we do that. Because we can't, install optical cameras inside a fan casing pulling 400-degree dust-laden gas.
No, the lenses would blind in seconds.
Yep.
They'd just melt or get coated in ash immediately.
So how do we make the invisible accumulation of dust legible to a maintenance engineer sitting in a control room?
Well, we shift our focus to the interaction between the fan blade and the air itself. We deploy high-frequency acoustic emission sensors and high-resolution electrical current monitors.
Oh, wow. So we are listening to the fan rather than feeling it shake.
Exactly. It represents a massive leap from simple vibration analysis.
Walk us through the physics of that acoustic monitoring. How does that actually work?
Sure. Consider the blade profile of a clean centrifugal fan cutting through the gas stream. It operates with a specific aerodynamic drag coefficient,
Okay.
and it generates a baseline acoustic signature like a very specific frequency of turbulence.
Right, the sound of clean wind resistance.
Yes. Now, as the sticky, high sulfur dust begins to microscopically plate out on the leading edge of that blade, the surface texture alters.
It gets bumpy.
It becomes rougher, more turbulent. The aerodynamic efficiency begins to drop infinitesimally.
The friction increases, which actually changes the sound of the wind resistance.
You've got it. Furthermore, because the fan now has to work slightly harder to push that rougher, heavier blade through the gas, the localized load torque on the drive motor increases.
So the motor is straining more.
Slightly, yes. The motor draws slightly more electrical current to maintain its rotational speed. By deploying high-resolution current sensors that sample at thousands of hertz, we perform what's called motor current signature analysis, or MCSA.
MCSA. Okay, so you have the acoustic sensors capturing the micro changes in wind turbulence, and the current sensors capturing the micro fluctuations in the motor's effort.
Right.
But, that raw data must be absolute noise. A cement plant is deafening. How do you isolate the sound of dust accumulating on a blade from the roar of the massive rotary kiln spinning right next to it?
That is the million-dollar question. And that is where the deployment of localized edge AI becomes the critical bridge.
AI.
Yeah, because you cannot send gigabytes of raw, noisy acoustic data from a remote plant in Madhya Pradesh up to a cloud server over Apache cellular connection to be analyzed.
The lag would be terrible.
The latency and bandwidth constraints make it impossible. Instead, you deploy an edge computing module.
So like a local brain.
Exactly. A ruggedized processor sitting right there on the machine running a specialized neural network.
So the AI isn't in some pristine data center in Mumbai. It's literally bolted to the steel casing.
Bolted right to the steel. The edge model performs localized feature extraction.
What does that mean exactly?
It uses fast Fourier transforms to mathematically filter out all the ambient plant noise. It filters out the rotational frequencies of the shaft, the gear mesh frequencies.
It strips away everything except what we want to hear.
Right. It isolates the specific high-frequency signatures of aerodynamic drag and the electrical anomalies in the current draw. The AI translates the raw physics of friction into a highly precise topographical model of the dust load.
And the operational outcome of doing this locally right on the edge is staggering.
It truly is.
Because by tracking the aerodynamic drag rather than the mechanical vibration, the system can detect the onset of the unbalance way earlier.
Yes, 72 hours before the mechanical vibration even reaches the trip threshold.
Here's where it gets really interesting for you listening. We are literally predicting the future 3 days in advance just by listening to the wind resistance on a blade.
It fundamentally rewrites the physics of plant operations. I mean, think about the strategic advantage of having a 3-day warning.
It changes everything.
The plant manager is no longer awoken by an emergency siren at 3 a.m. Instead, the AI flags the aerodynamic anomaly on, say, Tuesday morning. The reliability team calmly reviews the data, confirms the dust accumulation trend, and then they schedule a highly controlled, brief intervention for a scheduled downtime window on Thursday afternoon.
They can stage the exact replacement filters, the specific high-temperature lubricants, the scaffolding, and the safety permits all in advance.
Precisely. The kiln is brought down gracefully, which minimizes thermal shock to the refractory bricks.
And then the blades are hydrojetted or mechanically cleaned, the hatch is sealed, and the kiln is fired back up.
Nobody rushed. Nobody bypassed the safety protocol out of desperation.
It's just a regular shift.
Right. This encapsulates the philosophy of restorative engineering. The purpose of deploying Edge AI isn't to build a dashboard that looks futuristic.
No.
It is to leverage unseen digital intelligence to restore safety and agency to the physical workforce. It eliminates the reactive panic that historically defined the maintenance profession.
But let's pause and look at the operational bottleneck here. Because a 72-hour warning from an Edge AI is a massive technological achievement, sure. But if that predictive insight flashes on a screen and an engineer has to write it down on a piece of paper, walk across a massive dusty plant, and hand it to a mechanical supervisor who is already buried under 20 other reactive work orders.
The workflow collapses.
Exactly. The predictive value is instantly destroyed. Insight without workflow is just trivia. The AI data needs a nervous system to trigger actual wrench time on the floor.
And that's exactly where most predictive maintenance programs fail. They fail at the intersection of data and execution.
You can have the most sophisticated neural network analyzing acoustic emissions, but if the execution layer relies on WhatsApp messages or manual transcription into a clunky legacy ERP system,
It just doesn't work. This necessitates the implementation of a modern computerized maintenance management system, a CMMS like Oxmate.
Let's dissect the architecture of a CMMS designed for this specific environment. Because anyone who has worked in heavy industry knows the absolute hatred floor technicians have for traditional enterprise software.
Oh, it's visceral. Legacy systems were designed for accountants sitting at desktop computers, not for mechanical fitters wearing thick protective gloves in a 45 degrees Celsius dust-choked environment.
Okay, this sounds amazing, but you're talking about massive, dusty, chaotic cement plants. Does software actually survive contact with this kind of physical reality?
It has to, or it's useless. The UX design of industrial software dictates its compliance rate.
Meaning if it's hard to use, they won't use it?
Exactly. If a system requires a technician to navigate 5 nested drop-down menus on a tiny screen to close out a work order, they simply won't do it.
They'll just pencil whip the paperwork at the end of their shift.
Right. A modern CMMS survives the physical reality of a plant by being aggressively mobile first and deeply integrated with the physical assets.
And the deployment of heavy-duty QR codes on the actual machinery is the physical bridge we are talking about here, right?
Yes. Instead of forcing a technician to manually type in, a 14-character alphanumeric serial number for specific trunnion-bearing housing.
Which is prone to massive transcription errors.
Huge errors. Instead of that, they simply use their mobile device to scan this physical QR tag bolted directly to the asset.
And that single scan contextualizes the technician instantly.
Instantly. It pulls down the last 6 months of vibration history, the current acoustic AI predictions, the exact required lubrication volume, and the step-by-step standard operating procedure for the inspection.
That's incredible, and the data shows that this physical-to-digital bridge reduces transcription and identification errors by over 60%.
Easily. And equally critical is the offline capability.
Oh, right, because a cement plant is a labyrinth.
It's a labyrinth of massive steel structures, reinforced concrete silos, and underground galleries. Cellular signals just do not penetrate these areas.
A cloud-dependent app will just brick the moment the technician walks behind the preheater tower.
Exactly. So the CMMS architecture requires a local database cache on the mobile device.
How does that work in practice?
The technician downloads their entire route of work orders while they're in the control room Wi-Fi. Then they walk out into a complete dead zone, scan the QR codes, input the bearing temperatures, take photographic evidence of an oil leak, and close the work order.
All offline.
All offline. And the app utilizes conflict resolution algorithms to seamlessly sync all that data back to the central server the exact second they walk back into Wi-Fi connectivity.
So by removing the friction from the data entry process, you actually capture accurate field data.
Right. And when you feed accurate field data into pre-built preventive maintenance templates, which modern systems like Oxmate provide out of the box for standard rotary kiln setups, you dramatically accelerate the time to value.
You can go from paper to a fully digital PM schedule insanely fast.
In 14 days, you can go live targeting specific reliability metrics like pushing the ID fan bearing mean time between failures up to 6,200 hours.
Wow. But the value of a unified CMMS extends far beyond just organizing the mechanical team, doesn't it?
It does, especially when we look at the regulatory landscape in India.
Right, specifically the mandates enforced by the Central Pollution Control Board, the CPCB. The CMMS actually becomes an existential shield for the business here.
It really does. Let's talk about continuous emission monitoring systems, or CEMs. The regulatory environment has fundamentally shifted recently.
The CPCB no longer relies on annual manual stack sampling.
No. Cement plants are now mandated to transmit real-time data on particulate matter to SOx and NOx emissions directly to the regulatory servers in New Delhi.
But just transmitting the data isn't enough, is it?
No. The plant must legally prove that the CEMS analyzers themselves are being rigorously maintained and calibrated.
So if an auditor walks onto the site and the emissions data looks perfect on the screen, but the plant manager cannot produce the immaculate, time-stamped maintenance logs proving the bag filters were checked and the sensors were calibrated.
The plant faces severe consequences.
How severe?
They face a 30-day closure notice. They literally lose their consent to operate.
Wow. For a high-capacity kiln, 30 days of lost production is financially catastrophic.
It is a nightmare scenario. And historically, preparing for a CPCB audit involved weeks of frantic administrative panic.
I can imagine teams of engineers scouring shift logbooks.
Trying to piece together a coherent paper trail of calibration dates, struggling to read smudged handwriting, just praying there were no gaps in the record.
But the CMMS automates that audit trail entirely.
Completely. Because the workflow is digital, every time a technician scans the stack sensor QR code, performs the calibration, and hits complete, the system auto-generates a legally verifiable, time-stamped, geolocated compliance record.
So the administrative burden drops to practically zero?
When the audit arrives, the plant manager doesn't bring out boxes of dusty binders.
They just pull it up on a screen.
They execute a single-click export from the CMMS dashboard, presenting an irrefutable digital chain of custody for every piece of environmental compliance equipment on the site.
And this data isn't just trapped at the local plant level either.
No, and this is where it scales beautifully. For the executives at Ultratech or Shree Cement overseeing massive portfolios, the CMMS acts as a central nervous system.
Because the local maintenance team in a specific plant only sees the work orders they need to execute today.
Right, but the reliability directors and the corporate headquarters look at a multi-site portfolio dashboard.
Which eliminates the asymmetry of information between the plant floor and the boardroom.
Exactly. The central team can instantaneously compare the PM compliance rates, the predictive AI alarms, and the kiln availability across 20 different plants.
So they can spot trends that a single plant manager might miss.
Yes, they can identify systemic issues. For example, maybe a specific brand of bearing is failing prematurely across multiple sites. They can see that data and issue portfolio-wide engineering directives immediately.
Replacing the archaic, delayed process of monthly reporting calls.
Which nobody enjoys anyway.
Right. Okay, so we have established the edge AI sensors capturing the leading indicator and the CMMS executing the workflow. But, any seasoned maintenance engineer listening to this is waiting for the catch.
There's always a catch.
The catch is always integration. You are dealing with 30-year-old PLCs, legacy vibration monitors from a half-dozen different vendors, and entrenched IT networks.
It's a very messy environment.
Right. So the idea of just plugging in a new AI system into a running plant usually triggers absolute panic about network security and operational disruption.
And that hesitation is entirely justified. I mean, the graveyard of industrial IoT projects is just filled with startups who attempted a rip-and-replace strategy.
Meaning they demanded the plant tear out their legacy hardware to install proprietary closed-loop systems.
Exactly.
Yeah.
And a successful digital transition must meticulously avoid that innovation trap.
Yeah.
Massive, disruptive changes introduce unacceptable risk.
So what does this all mean? How do you actually wire this up without breaking the plant? Let's walk through the phased approach to PLC sensor integration.
Okay, so phase one has to be zero risk. Phase one respects the capital already invested in the plant.
The facility already has legacy vibration monitoring systems wired into the DCS. They already have CEOPS hardware.
Right. You do not touch the hardware. Instead, you build a data bridge using standardized, highly secure industrial protocols. The industry standard for this IT-UT convergence is OPC-UA.
OPC-UA, which is Open Platform Communications Unified Architecture. Contrast that with the consumer-grade APIs people might be familiar with. Like, why is OPC-UA the absolute backbone of industrial integration?
Because OPC-UA is designed specifically for the deterministic, high-security requirements of industrial automation. It doesn't just pass raw numbers.
It passes context.
Exactly. Complex data models with deep semantic context. It ensures that when a Siemens PLC sends a temperature value, the receiving CMMS knows exactly what sensor generated it, the engineering units, and the timestamp down to the millisecond.
And it does this securely?
Very securely. Through encrypted pub-sub architectures that protect the critical OT network from external cyber threats.
And alongside OPC-UA for the local machine data, the architecture uses REST APIs to pull the higher-level CMS data and cloud-based analytics into the CMMS.
Right. So by establishing these bridges, phase one simply digitizes the existing workflows. It means you aren't throwing away your old alarms. You're just teaching your system to speak a new, smarter language alongside the old one.
The maintenance teams just start using the mobile app to conduct their routine oil analysis sampling and manual CMS readings.
Exactly. The workforce becomes comfortable with the mobile interface, the QR codes, and the digital work orders without having to interpret any new, confusing AI algorithms right off the bat.
You build cultural adoption through low-friction utility.
Yes. And once that cultural baseline is established, you initiate phase two. You layer in the intelligence.
Which is the physical deployment of the edge AI hardware on the ID Fan.
Right. You mount the acoustic and high-resolution current sensors. But instead of creating a separate, isolated dashboard that the operator has to monitor, which they hate,
you feed that new leading indicator data directly through the established OPC-UA bridge into the CMMS.
Exactly. It merges with the legacy data.
So it creates a unified digital twin of the asset's health condition.
Yes. On a single screen, the reliability engineer views the traditional lagging vibration trend line mapped directly alongside the predictive leading acoustic drag curve.
And the power of that visualization is immense.
It's undeniable. The engineer can literally watch the AI detect the aerodynamic friction days before the vibration sensor registers a single anomaly.
It builds absolute trust in the system because the operator can see the AI's prediction validated by the legacy sensor's eventual alarm.
Right. This phased, incremental integration avoids overwhelming the workforce. It empowers them by gradually increasing the resolution of the data they use to make decisions.
Okay, so strategy, software architecture, and AI models are conceptually beautiful. But execution requires capital, and capital requires board approval.
The hardest part.
If a reliability manager is listening to this right now, convinced that this is the path forward to escape their run-to-failure nightmare, they face a massive hurdle. They have to walk into a room of financial controllers and justify a budget for technology that sounds like science fiction.
It's a tough sell on paper.
So how do they prove this works without asking for a massive CapEx approval up front?
The playbook for overcoming that institutional skepticism requires a highly targeted, undeniably physical demonstration.
A pilot program.
Right. The literature refers to this as the 48-hour asymmetric bet. It is a tactical maneuver designed to generate undeniable proof of value with minimal financial risk and zero operational disruption.
You're basically setting up a race between the old technology and the new technology on one single machine. It's a low-risk, high-reward test. Walk us through the exact execution of this pilot.
Okay, so you do not attempt a plant-wide rollout. You isolate a single, critical, historically problematic choke point. You go straight to the most heavily degraded ID fan in the plant.
The asset that causes the most late-night phone calls.
Exactly. And you bypass the complex IT networking completely for the pilot. You take a single, battery-powered edge compute sensor, typically housed in a rugged, bead-blasted aluminum casing with high IP ratings to survive the dust and heat.
And you just stick it on there.
You magnetically mount it directly onto the bearing housing of that specific fan.
So the installation takes minutes, not weeks. No wiring, no shutting down the kiln, no hot work permits.
Nothing. Over the next 48 hours, the plant runs normally. The Edge AI establishes its localized baseline, learning the specific acoustic signature of that fan's normal operation.
And then it starts hunting.
Right. It begins analyzing the high-frequency microfluctuations in the aerodynamic drag caused by the high sulfur dust.
And because you pick the most problematic fan, the unbalance is practically guaranteed to start forming.
Exactly. You capture the telemetry from the Edge AI and you plot it directly against the data coming from the legacy DCS vibration sensors. The resulting graph is the undeniable proof you take to the board.
Because the graph will visually demonstrate the acoustic drag curve spiking upwards, indicating the mass accumulation, hours and days before the flat line of the vibration sensor finally jerks upward into the alarm threshold.
The data makes the invisible forces visible, and when you present that graph to the financial controllers, the conversation shifts from the cost of the software to the opportunity cost of the lost production.
Right. You attach the financial reality to the graph.
Exactly. A two-kiln plant that manages to reduce unplanned ID fan stops by just 68% through predictive scheduling saves between 4.8 and 9.6 crore rupees annually.
In just lost clinker and emergency repair costs.
Yes. When you put a 9 crore operational savings next to a graph that physically proves your ability to predict the failure 72 hours in advance.
The budget for the CMS and the broader sensor rollout is approved instantly.
Instantly. The asymmetric bet leverages a tiny initial effort to unlock massive systemic change.
We have mapped the entire journey today, from the brutal thermodynamics of the rotary kiln to the sophisticated algorithms of Edge AI, and finally, to the financial mechanics of the boardroom.
It's a full-stack view of the problem.
But the most profound element of this transition isn't technical. It's the philosophical shift in how we approach the maintenance of critical infrastructure.
Yes.
It's easy to get lost in the numbers and the AI, right? 380 million tons of cement, 9.6 crore in savings. Neural networks processing thousands of data points a second. But at the exact center of all that massive scale is a human being holding a wrench.
Exactly. And the foundational texts on restorative engineering emphasize this relentlessly.
At the end of the shift, this is about making sure people don't get hurt because a machine was pushed past its breaking point.
That is it. The ultimate metric of success for deploying this technology is not merely maximizing equipment uptime or optimizing the MTBF, although those are the financial drivers. The true metric is the reduction of human risk.
It's the elimination of the 3.00 a.m. emergency call.
It's the difference between an engineer calmly reviewing an anomaly on an iPad on a Tuesday morning and a frantic crew being pushed to a 400-degree hazard zone with alarms blaring on a Sunday night because the system suddenly shook itself to death.
When you transition a plant from a lagging indicator run to failure culture into a leading indicator, predictive culture driven by an intelligent CMMS, you fundamentally alter the psychological environment of the workforce.
You replace a posture of constant reactive fear with a posture of precision, control, and scheduled safety.
As one of the operational logs summarized so perfectly, the millions in savings mattered to the board. But for the shift supervisor, the text message home to their family saying, "I'm safe tonight, the shift is quiet," mattered infinitely more.
Technology, when applied correctly, restores the dignity and safety of the human operator.
That's beautifully said.
Operational excellence demands that we stop normalizing chaos. The most catastrophic system failures in heavy industry, and indeed in any complex system, rarely happen instantly.
They begin as microscopic, ignored anomalies.
A slight increase in wind resistance. A skipped lubrication route because the paper logbook was lost. The muddy waters of poor data.
By adopting the discipline of capturing the leading indicator and tying it to an automated workflow, engineers take definitive ownership of the system's reality.
It forces the invisible frictions to become visible before they tear the machine apart. It is the ultimate expression of control. You are no longer a victim of the machine's sudden failure. You are the architect of its continuous operation.
If you are managing operations right now, whether you oversee a massive cement kiln, a fleet of logistics vehicles, or even a complex software deployment team, the blueprint is right in front of you. Stop relying on the vibration alarms.
Stop waiting for the catastrophic shaking to tell you the system is broken.
Deploy the intelligence to capture the microscopic frictions early, build the digital nervous system to route that insight to the people who can fix it, and execute that 48-hour pilot to prove the ROI to your skeptics.
The technology exists today to predict the failure of a massive steel impeller, simply by listening to the changing friction of the wind against its blades. That level of predictive precision is available. The challenge is entirely in the willingness to adopt it.
It really is.
I challenge anyone listening to examine their own operational bottlenecks. We just discussed how technology can predict a massive mechanical failure 3 days in advance simply by listening to the friction of the wind on a blade.
Yeah.
Think about your own daily operations outside of the factory floor. What are the invisible frictions in your workflows, your team communication, or your personal habits that are screaming to be measured before the whole system shakes?
Find your leading indicators before the structural damage is done. Dig into the physics of your own bottlenecks and don't let the scale of the problem prevent you from running that first localized pilot. Thank you for taking this deep dive with us.